have a bill. It's the great pleasure of introducing Wendy Freedman again. She is the John and Marion Sullivan University professor, 20th University professor that this university has had. And I'll remind you, boy, does time fly when you're having a really good time. She joined us in 2014, so she's beginning her third year. And of course, before that, Wendy was at the Carnegie Observatories for 30 years. I'm not sure how the math all works here. 12 years as a director. One of the things that she's most proud of is that she was born in Canada and holds dual citizenship. I have no idea why, but she told me that. I guess so. Wendy has many honors. She's a member of the National Academy of Sciences, the American Academy of Arts and Sciences, the American Philosophical Society, and I only have breath for one more, the winner of the Gruber Prize. She's most well known, I think, for two things: reining in the Hubble constant and establishing a reasonable error budget. And I think she's going to tell us the difference between accuracy and precision. And that was a big problem with the Hubble constant because we used to have very high precision measurements. And so she's reduced the precision but increased the accuracy. And I'm going back 30 or 40 years, a lot longer than the students can remember. And initiating, oh, there's a picture of the GMT. But one thing I bet you don't know is that her TED Talk on the GMT has 1,146,268 views. And that is only a factor of 2 smaller than the number of followers that Donald Trump has. So I'm very excited to hear Wendy's talk today because the Hubble constant, which is arguably the most important parameter in all of cosmology, and she reined it in, all of a sudden it's become extremely interesting again, and she's going to tell us why.
Michael, I can't believe it's been over 2 years that I've been here either, but this quickly has become my home, and I really am enjoying being here at the University of Chicago. I think that the measurement of cosmological parameters is really one of the success stories of the last couple of decades, and we didn't use the words precision or accuracy with cosmology 2 decades ago. And I think it's our own Mike Turner who coined the phrase cosmology. And yesterday he took me to task in a meeting and said I had the wrong title. It should be increasing precision in measuring cosmological parameters. But we'll get back to that in a second. So why the success story? And I think there are a number of factors that led to why we can measure the Hubble constant with both increasing precision and accuracy. And one of those is development of a number of techniques for measuring distances to galaxies and being able to address systematics, which really, that was the crux of the problem, systematic errors. Even though people had realized there were things like dust and that reddening was a problem, no one corrected for it. And it was a development of, it was 2 things, development of CCDs and infrared arrays, and then the launch of the Hubble Space Telescope that allowed us to address these things for the first time. And now with the new tension that's arisen with the Planck data, we're at a similar kind of juncture. We will not be able to get beyond systematics without another jump in precision and accuracy. And the nice part about that is that the Gaia satellite, which is now flying near its launch, and the first data release happened this September, doesn't yet have the precision or the accuracy for the solving of this tension that has arisen, but it will by the time the final data release comes out, and I think probably next year they'll have something interesting to say. And then the second thing is the imminent launch of the James Webb Space Telescope, and that will happen in 2018, so it really is just over a year away, kind of amazing. So if we get to this question of difference of precision versus accuracy, you have to figure out which button needs to be forward. For the benefit of Mike and any students here who haven't yet learned the difference between precision and accuracy, You can be very precise and, this is the laser pointer, but way off target. And so if we don't correct for reddening always makes objects appear dimmer than they actually are. You're going to think that your object is farther away than it actually is. And so what you need is both precision and accuracy, you hope. And that really was what held up why we had this factor of 2 uncertainty for so long. So what people may not realize is that there's not only tension amongst the results from Planck and the Cepheid plus supernova results, but there's also tension in H0 here at University of Chicago. So here is our own Wayne Hugh, the Horace B. Portman, professor of astronomy and astrophysics. And Wayne, for a very long time, has been publishing and making the case that if we could measure the Hubble constant to a few percent or better accuracy, you know this, then at redshift of 0.5 or so, this is one of the best constraints in combination with CMB measurements for the equation of state W. And then we have the dynamic duo, dean and director, a lot of deans. And Mike is telling us precision is enough. And Rocky says H0 is just a nuisance parameter and you're marginalized over it, why bother measuring it at all? So what I'd first like to do is review a little bit what the status of the current cosmological model is, where the CMB results and what they're getting, and argue that higher accuracy in H0 really would be very useful to address this tension that's arisen. And then I'll talk about how do we measure the Hubble constant, what do we need to do to get that next level of accuracy. And I'll start first with some history because I think it's important for the context of how did we overcome the systematics early on. And then I'll move to progress since the Hubble Key project, 15 years, a lot of progress in measuring distances of galaxies and overcoming further systematics. And then I'll talk to you about our recent work with both Hubble and Spitzer as part of the Carnegie Chicago Hubble project, the CCHP. And then I'll go on to talk about how we can improve things in the future. So here's the issue shown graphically here. And so this is just the values of the Hubble constant as a function of time since the Key project. So we got a value of 72. It was based on 5 different secondary methods, and it was essentially calibrating those methods with the Cepheid period luminosity relation, or the Leavitt law, and for the first time being able to calibrate a number of different methods and essentially average over the systematics of each of those methods. And the first CMB results, WMAP here, published in 2003, that measured H0 accurately again, it got a result in very good agreement with the Key project. This is a plot put together by Rachel Beaton in our group in a paper we just published, but shaded. Wayne, who brought his nice plot talents to show how the errors really had changed over time. So the value that is coming out of the Cepheid plus supernova, so when I refer to direct measurements of the Hubble constant, what I'm talking about is local measurements, measurements of the Cepheid distance scale applied to type 1a supernovae. So the error bars have come down quite considerably since the Key project. And in the case of the CMB measurements, not just the errors, but also the value has been going down. And based on the most recent Riesedal paper that was posted a few months ago, and the Planck 2015 results, that formally is a 3.4 sigma difference. So the tension appears to be getting worse, not better. And that's certainly what we're also seeing. So just another summary that breaks down in terms of distance ladder measurements. Georgia Staffu reanalyzed the Riesedal data, and Riesedal includes Dan Skolnick, who's probably somewhere there you are, who's a very active part of that group. And so those values are, even with the reanalysis, 70 or so or higher, 73. The Planck results are giving a lower value, more like 67, assuming a flat lambda CDM model. And so emphasize that the Planck results are not a direct measurement. You have a fit with a lambda CDM model, and then you derive the value of omega matter, H naught, lambda, and so on. And then there's an effort to establish an inverse distance ladder using baryon acoustic oscillations, but again, using the Planck constraints and assuming that you have standard early universe physics with 3 neutrino species, an effective number of neutrinos of 3.046, the standard value. So those built-in assumptions, and then you can estimate the Hubble constant. So these are the values, 67.8 with an uncertainty of 1.3% coming from Planck, and then the direct local measurements with Cepheid about 73 or 74. So the error bars in both kinds of determinations are decreasing, but the tension is worsening. So what do we make of the current tension? And of course, we need to understand whether or not there are systematic errors that are affecting one or both of the determinations. So what could it be in terms of the distance scale? And the Cepheid 0 point is something that, of course, sets the scale for the determination of H naught applied to supernovae, and that affects both groups, the Reese et al. And our own Kearney Chicago group. So there are 3 methods right now that people have been using to calibrate the Cepheids. And the first is using a sample of Cepheids in our own Milky Way. And to date, there are parallaxes that have been measured using the fine guidance system on Hubble. But it's a very small sample, it's about 10 objects. And Adam and Casatano and others have added 2 or 3 more objects since a paper by Fritz Benedict and a number of us did the study of the 10 earlier on. It's a very nice sample in terms of, I'll get to that, I'll show you the data in a moment, in terms of small scatter and period luminosity relation. And the Milky Way is a spiral galaxy, much like the galaxies that have type 1a supernovae in them, so there aren't differences in potentially in chemical composition and so on. And the uncertainty currently is about 2%. The other is the Large Magellanic Cloud, and this is the object that we used for the key project as a calibration. These have been very well measured as a large sample of long period Cepheids, similar to those in the other galaxies that we're looking at. The uncertainty there is about 2.5%. And then NEC 4258, this is a spiral galaxy, it has a black hole at the center, and it has water masers. And so by measuring the rotation curve, it has a Keplerian velocity curve, you can estimate, and also proper motions you can measure for the water masers, determine a geometric distance to the galaxy. So each of the different methods has its own strengths and weaknesses. The Milky Way, of course, these are good analogs to the Cepheids in other galaxies, but it's a small sample right now. That is going to dramatically change with Gaia. The LMC, lots of Cepheids, lots of long period Cepheids, but a smaller metallicity than the spirals that it calibrates. So if it's not possible to calibrate a metallicity effect, if there is one, and in the infrared it appears to be very small, but it's a systematic that you have to address. And NEC 4258, there's one galaxy, exactly one in the sample of objects that have maser distances measured. Very difficult to determine what the systematics are in this method, and the value of the distance of this galaxy really has been moved by much more than the error bars that have been quoted for it. But nonetheless, the uncertainties are at 50%, and these are 3 very independent techniques for getting the 0 point. But if you're going to talk about percent precision, percent accuracy, and Planck now has set the bar very high, then these are the kinds of systematics that we need to improve. Second, there are very few independent checks on the Cepheid distance scale. So right now, all of the H0 determinations locally really are dependent on the Cepheids applied to type 1a supernovae. So if there are issues with the Cepheids, for example, differences in chemical composition that are contributing to systematics, and at the 1 to 2% level, that can be a big factor, then we won't know unless we have an independent way of measuring, of testing against Cepheids. And then there are small numbers of objects. Type 1a supernovae are very rare. They go off about once a century in a galaxy. So in the small volume that's accessible to us to measure Cepheus with HST, it's even smaller number of objects where you have type 1a supernovae that you can then go and measure Cepheus to. Good Wendy. Okay. So increasing the numbers of calibrators is something that we'll want to do, but it's difficult given how rare supernovae are. Well done. In terms of the CMB anisotropy, as I said, the H-naught estimate assumes a model. You don't want to assume the model, you want to actually measure the whole constant. And if there is something additional missing, missing in the model, then measuring H-naught accuracy is a way to constrain the model and determine if there is additional physics beyond the standard. It's been pointed out that there's a discrepancy between low L and high L measurements of the spatial scales of the CMB results. I'll show you that in a moment. And depending on which data set you use, you do find a significant difference in H-naught. So if you could establish that the systematics had been addressed, you had H-naught to 1% or better, how would you explain that? And there are a number of different ways people have looked into these for doing that. None of them appear particularly promising at the moment, I would say. But for example, if you had a different equation of state for dark energy, W is not equal to -1, that would be one way of explaining it. And one thing that I should say, and we'll show you in a moment, the trade-off between amongst various of the cosmological parameters is fitting the CMB data allows for interplay and very different values of cosmological parameters, different combinations of those. You could have another relativistic species, for example, an additional neutrino or some other what people are referring to as dark radiation. A lot of effort has gone into exploring that possibility, decaying massive dark matter particles as a possibility, and then probably more exotic non-zero spatial curvature, or some form of a modified gravity. So this audience doesn't need much background in CMB anisotropes, but not everybody thinks about this on a daily basis. So of course you measure temperature fluctuations in the microwave background. You can expand those in spherical harmonics, and what's shown here, commonly shown, is the power in micro-Kelvin squared units, and this is logarithmic interval shown here. So you have small spatial scales to the right, large to the left, and so at low L, your power here is such that you're looking at about 30 microkelvin, and then this first peak is at a multiple value of about 200. That's a 1 degree scale and has about 6 times the power. And these are the recent results from Planck, including ACT and SPT data. And as we all know, the 6-parameter CDM model is an excellent fit to the data. You now have 8 peaks essentially measured in the angular power spectrum. So it's really a huge, beautiful data set. Now, of course, it's possible to measure lensing. I wasn't here Monday for Blake Freedman's talk, but we talked about measuring lensing from the CMB. And of course, E-mode has been measured really well on peaks in the power spectrum for E-mode polarization also. So here are the 6 parameters that go into the fit. 2 densities, virion density and the cold dark matter density. And those each are, what you measure is omega b little h squared. And so for the younger people in the audience, of course, still H squared came about because we didn't know H naught better than factor 2. But that's still an issue here. There's a real geometric degeneracy, and you don't measure those parameters independently. Then is the angular size of the sound horizon, the optical depth, the scalar spectral index, and then the amplitude of scalar fluctuations. So given those 6 parameters fit, then you can derive other cosmological parameters like H naught and omega matter, omega lambda, and W. So the temperature and lensing data yield a value of a constant of 67.8, matter density of about 0.3, lambda 0.7. And from temperature and lensing data alone, you don't have very tight constraints on W. But if you add in VAO and supernovae, and then this is the H naught that Georgia staff determined reanalyze and reset all data, then you get a value of W that is consistent with if you use type 1A supernovae and VAO or other measures of mega matter. So this just illustrates some of the degeneracies. So these are some of the samples from the Markov chains. This is H naught as a function of effective number of neutrinos from the 2005 Planck results. And the color bar here indicates the value of sigma 8. So you can see that as the effective number of neutrinos, it doesn't have to be neutrinos, any relative species increases, then the value of H naught increases. So, once again, it's not a unique solution. If, for example, you determined that the Hubble constant was 73, you would get a fit to the CMB data, and other parameters would move to accommodate that. And here, color-coded by H naught, is this is the equation of state, the evolution of the equation of state, and the current value of W, degeneracy with the Hubble constant. And this is just illustrating further. So here's from the Planck cosmology paper, color-coded. In this case, these are in gray. Contours come from the temperature, the low polarization data, and then adding in successive here polarization of TE and E, and blue adding in VAO. So this is the dependence on H naught, and then these omega baryon, omega cold dark matter H squared for the various parameters shown here. And you can see flatness does not come from CMB alone. Some of neutrino masses, there's a degeneracy with H naught, effective number of neutrinos as we've seen. So just a word on baryon acoustic oscillations. So of course you have fluctuations in radiation. You also see corresponding fluctuations in the matter power spectrum. And the BOSS survey, for example, now has measured several peaks. And you wish that it was this easy and you just looked on the sky and measured the big rings and you could see the angular size of the sound horizon. But statistically you could do this, but it's really not that simple.
So, regarding the previous slide that you showed, it seems that you can always approach the measured values locally, but by worsening the field. Right? For instance, if you increase the masses of the
increase the number of the parameters, you're gonna, yeah, absolutely. No, and I think the fair statement is you fit the Planck data really well with a 6-parameter fit. There's no indication of any other parameter. I think that's a fair statement. And this, looking at the sum of neutrino masses, again, sampling from our Markov chain. So this is H naught as a function of sum of neutrinos. So if you only have the temperature data, add in the lensing from the CMB, and then add in VAO, you do successively better. And so without VAO, your limits are about half an eV, and the best estimate at current time, 95% confidence limit, is something like 0.23 eV. So Addison et al. Looked at the Planck data and separated out. If you look there is a significant difference between the high L and low L data, and it's greater than 2 sigma. The Planck group looked at this even more recently and made the case that the difference at low L really is being dominated by modes less than 30, where the power is known to be low. If you exclude L less than 30, then the discrepancy isn't as large as seen here. But in any case, that's something that really hasn't yet been well understood, and there's still a difference. Now here, baryonic acoustic oscillation data that shown here on the left, these are measurements for galaxies in red, and in blue are new Lyman alpha VAO treatments. So this is a matter versus the Hubble constant. Here's Hubble constant versus effective number of neutrinos, and the black contour here is from Planck. And you can see that the Lyman alpha data are tending to tending to higher values of H naught. And I don't think people really understand the reason for the discrepancy yet. There's many more galaxy data, but we don't know yet how that will resolve. It's the same authors, but they changed the color scale on this side. So red now is Lyman alpha, and green is VAO plus Planck. But again, making the point that these parameters really are degenerate. And then, to your point, Carla, if you increase the number of parameters, then you can allow for more physics, but you don't learn anything. The constituent error bars get bigger. So this is what they're calling an extended CDM model, this group, and they do a 12-parameter fit. And what they know is that the biggest effects, your constraints on the Hubble constant really are not very useful at all, nor on sigma 8, and even when you include the VAO data. So if there is additional physics, you could be hiding it just because Lyman CDM with 6 parameters is a good fit doesn't mean that's a complete model. And then finally, Bernal, Verdi, and Rees recently made the case that you could do an inverse look at this issue. And you noted that what you're measuring with VAO is essentially the sound horizon times little h. And so you can say that you're willing to assume lambda CDM is really the universe, standard number of neutrinos, etc. And then the size of the sound horizon you measure is 137 megaparsecs. Alternatively, you could say, okay, we know what the value of H naught is. You measure that to be 73. You don't make any assumptions about the early universe physics, and then you can break the degeneracy in the product, and you end up with a sound horizon that's smaller. So there is room if you were to establish that H naught to high accuracy is 73. There's room for that degeneracy to be broken. Okay, so just before I go on, I think just stating the obvious, we do have a standard model, but it isn't like the standard model in physics that's been well tested in the laboratory. We have no clue yet what the dark matter is. We don't know anything about the dark energy, let alone whether it evolves with time. There's no theory, and we don't understand inflation or what drives inflation. And so to assume that we have a complete model is probably premature. And measuring independently values for the Hubble constant is a way that we will be able to constrain the model. And that is the way to do it, without assuming you know what the model is. Okay, so let me turn now to measurements of the Hubble constant and a little bit of history, where we are, and what improvements are coming to your horizon. So, for those of you who are under in the audience, didn't live through this, there really was a period where we didn't know the Hubble constant better than a factor of 2. Values early on that Hubble and others measured were up in the 500 range, and then Walter Baade was not able to measure Baade libraries in the Andromeda galaxy. Exactly, detected were giant branch stars, which we'll talk about in a moment, and that resulted in about a factor of 2 decrease in the Hubble constant.
What was
And
the meaning of those symbols?
what's the meaning of them?
Yes.
It-
I mean, it looked like they were off by
Yeah.
several standard deviations.
Yeah, so in this case, it was because here they thought there was only one kind of Cepheid variable. There turned out to be two different kinds, a low mass and a high mass kind, and they just didn't know. So it's unknown systematic, and that's what's bitten every time in terms of determination of Hubble constant. And then, this, I'll show you a blown-up version of this, from the mid 60s to 1990, where there's this factor of 2. That was systematic again. Some people corrected for reddening, some people didn't. It was based on photographic photometry. These were nonlinear detectors, saturation effects at high light levels, reciprocity failure at low light levels, just a number of things that, there were no Cepheids that were measured for type 1a supernovae because they were just too far away. Without Hubble, you couldn't even be. So a number of reasons, but the error bars did not overlap, and that's where we are now. There's been considerable improvement, but I think, again, sorting out the differences between 67 and 73, it's like here, you need to be able to get another jump in technical capability to dig in and see whether they're systematic. We just don't know about right now. So to the extent that we've tested, we don't see any systematics that could be affecting values in a moment, but until we get better capability, there's no way really of testing yet. So the key project was designed to measure Cepheid distances to galaxies to high precision and accuracy, obtaining data at an optical waveband and also near infrared band so that you can correct for reddening, which had not been done. So in the 80s, just before Hubble was launched, the distance to the nearby galaxy, M33, the Triangulum galaxy, was uncertain to a factor of 2. So even nearby, it was really not well known. And this is for the theorists in the audience. It's really easy to find stuff. You just look at a picture and make a leap and jump right out of you. But the nice thing about Hubble was that we could design an observing strategy. So people like Sandy and Bada would literally go to the 100-inch or 200-inch and take hundreds of photographic plates to be able to get enough time coverage and accuracy to be able to pull out the periods of the Cepheids and luminosities. But with HST, because we knew that the weather was always going to be clear, we could do essentially a power law spacing and find the Cepheids and the periods within a 1-year window. 2 months, actually, most of the time within the continents, observation a year later. And this is a logarithm of the distance versus log z, and really the first time that you ever could put the different distance indicators onto one plot. So here are the HST data for the Cepheids, and the green points here are the type 1a supernovae. And as I said, before HST, there were no calibrators for type 1a supernovae. And that really changed the whole game. And this is just the probability the density distributions for the different methods that we used. And so the Gaussians here are representing the statistical uncertainties for each of the methods, the cumulative probability distribution, and the error bars here reflect the systematic errors of the different methods. And it was really the fact that we had different interlocking methods where we could test the Cepheids locally, we could test the supernovae at greater distances into the level of 10%, which is what our final result was. We could give a very robust measurement of the Hubble constant and its statistical and systematic uncertainty. This is just velocity as a function of distance and the deviations from a fit.
What's the bump that's offset up around 80 something?
That's surface brightness fluctuations. So that's these galaxies here, which were elliptical galaxies in clusters like the Virgo cluster and the Fornax cluster. So these galaxies, we would measure surface fluctuations have been measured in elliptical galaxies, and the spirals are the ones that set the distance scale where you can actually measure calibration. So you can see the error is very large. But no matter how we combine them, we did a Bayesian analysis, we looked at classical frequency techniques, and no matter what we did, it wasn't dependent on how we did the statistics. Okay, so what's the current status? And as I said earlier, right now we really are relying on Cepheids plus the type 1a supernovae, and that's true for both groups doing this work right now. The Cepheids do have some checks. There is the major galaxy in 4258, and there are a few eclipsing binaries in nearby galaxies like the LMC and M31, but not a lot of detailed checks. And at the time of the project, we had many galaxies, and the distances had been measured by many independent techniques, and then we really could average them in the systematics. So let me show you the data since the KEY project and where we are in terms of systematics and what we need to do to get to that next level of percent precision and accuracy. So we started a few years ago the Carnegie Hubble project to test the Cepheid calibrations using Spitzer. So Spitzer is a sister satellite to Hubble and operates in the mid-infrared and has a number of advantages for studying Cepheid, for example. The reddening is negligible. So the absorption is 17 times smaller than in the optical. The dispersion in Cepheid through luminosity is between a factor of 2 to 3 smaller than it is for the optical. So the precision, again, that we can measure distances is greater, and theoretically the effects of metallicity are predicted to be very small, but it's a question that we can ask and address empirically to see whether or not that's the case. And so here are data for the Cepheids in the Milky Way. This is a sample that has parallax measurements from HST, and so these are 3.6 micron observations of pure luminosity relation. And these are data for a very well-observed sample of Large Magellanic Cloud that we had observed from the ground. They had extensive optical photometry, and then we observed them at Las Campanas in the near-infrared, and then we added the Spitzer observations. So the first thing to note is, so one of the concerns with the Milky Way sample, very small, you might be worried, we are worried that the dispersion might not be reflecting the true dispersion. If you just have too small a sample, you might be unlucky and get one edge of the instability strip. But it matches very well with that of the LMC, where the sample is almost 100 stars. And the dispersion is a tenth of the magnitude. That's 5% distance for a single, for the entire sample. And of course, per star, it's much smaller. And here now, these are the 10 stars that were observed by Benedict et al. Of HST and published UV and optical data going out into the infrared for this set of stars. And so this will soon be superseded by Gaia. As I said, very small data set, but agrees very well with LMC. And I should point out that it gives, if you use that calibration, gives a distance modulus, the LMC of 18.48, which is within 1% of the value that we used at the time of the KEY project. So no indication at this point that there's a big change in 0 in the way that Walter Bonnet discovered, for example, going from 500 to 200. So here are the data in the near-infrared J-band at 1.6 micron, 1.2, H-band 1.6, and K-band 2.2 microns. So these are observations that we got at Las Campanas using the 1 meter telescope there, and these are data from the Spitzer Space Telescope. And if you look at the residuals, the deviations from the fits, you can see that they correlate. These are space-based observations, these are ground-based. And the correlation is real. It actually is reflecting the geometry of the Large Magellanic Cloud. And you can measure the geometry by measuring the offsets from red data. Reddening is very simple to correct for with multi-wavelength data, and then you can also test for differences in metallicity. And I apologize for this, I went looking for this plot. Resolution is awful, but here are the data for NGC 4258, and so now we're moving out to 7 megaparsecs. LMC is at 50 kiloparsecs, and the dispersion in the PL relation is larger. It's 0.36 magnitudes. And this is the closest galaxy for which there's a Cepheid and a supernova distance. So here are the period luminosity relations for the set of galaxies that calibrate the type 1a supernovae. And this represents a huge increase. So this is the Resedal paper from 2016, and the 2011 paper had only 8 calibrators. So, but we're really pushing now in terms of what can be done with Cepheids. So for example, here's 4424, and it's about 16.5 megaparsecs. So the issue is crowding the individual Cepheids. You have to find them in the disk of the galaxy, and in fact what's crowding the Cepheids are red giant branch stars in the disk. So Cepheids are young stars, you only find them in spiral arms or the regular galaxies too, but not elliptical galaxies, not in the halos of galaxies. So the average dispersion here is about 0.4 magnitudes compared to the LMC, where it's 10th of a magnitude. So there are several ongoing programs to find supernovae in the local universe. It's harder than for the distant universe, and you have to do this individually, go from galaxy to galaxy, where the high redshift you can sit on a frame and you get several galaxies simultaneously. But a lot of effort, our Carnegie Supernova Project, Pan-STARRS, the Center for Astrophysics Group, and a number of others, also amateurs, have been finding nearby supernovae and increasing that sample. Dan Skolnick undertook a heroic effort to bring the various projects onto a common calibration. So people were using different standards, and very hard to compare results amongst the different groups. And so he standardized a sample with a redshift range of 0.02 to 0.15. And the new data, there's multi-wavelength data, important again for correcting for reddening, and the dispersion in the supernova Hubble diagram is about 0.12, particularly well determined as you go further to the red. And just to remind you what you do in the case of type 1a supernovae, they're not perfect standard candles. They don't all have the same luminosity. The luminosity at their peak correlates with the rate at which they decline from their peak magnitude. And it's not unlike Cepheids. The brighter objects decay more slowly. For the Cepheids, and brighter objects have longer periods. But you can correct for that. One group uses a stretch factor, and you can correct them to a common magnitude at peak, or you can use the slope in the decline rate, which other groups have done. This is a sample from Bertul et al., and here they're quoting a dispersion of 0.15 magnitudes. Here's the low Z sample that we can use for H-naught determinations, and as you go farther, that's those are the data for which you can constrain nucleation states. So I'm going to say a few words about Carnegie Supernova projects, because that's the effort that I'm involved in, and we've been observing for over a decade now at Los Campanas, and the idea is to use the smaller telescopes. It's not a survey program, it's a follow-up program, so many other groups were doing the actual discovery of supernovae, but once you find a supernova, then you really want to be able to observe it in some detail with really good cadence so that you don't have gaps in light curves, and also with multi-wavelength coverage. And so that's something we're ideally suited for at Las Campanas, to follow with the smaller telescopes, and when needed, spectroscopy with the Magellan telescopes. And we also did, I won't talk about it today, but an I-band Hubble diagram using supernovae out to redshifts beyond 0.5 to look for systematics in the supernova results. And so, as I said, we used all of the telescopes on the mountain, multi-wavelength photometry and spectroscopy, and really well-observed light curves. Mark Phillips is the PI of that low redshift effort. And there's a second part, which again involves optical photometry, but this time also a component to follow up in the infrared, the fire spectrograph on Magellan. And this is a data set which is going to be very useful for W-FIRST, for example, like a comparison sample at low redshift for the high redshift supernovae that will be found in future with W-FIRST. So just to give you some examples of, here's a light curve, and it really is a typical light curve. You do catch them before maximum, and very few gaps. Bluff Lagoon is an ideal site to do this. The weather is very good. We had 9-month campaigns that were centered over the summer, so avoiding the winter, June, July, August, when the weather is bad, and it allowed us to put together a data set of templates, and with the multi-wavelength data to correct for reddening K corrections. The K corrections were not well determined in particular, and look for evolutionary effects. So it is, I think, the most extensive data set for dealing with systematics. Again, if we're going to push down to percent level, you need to worry about systematics. Here's an example of spectra. So the supernovae, their spectra vary widely as the supernova evolves. So this is epic here, minus 15 days in purple, going to 45 days here in red. So these bands are moving through the band passes you're observing with, and the K corrections can be quite large. So the spectra, again, were taken, this is a sequence over time, so that we didn't have to do large interpolation. So the observing is now finished, and there's a third set of data that we're just about to release. This is the I-band Hubble diagram, and some of the low redshift data here is what we can use to constrain the Hubble constant. And based on this first sample here, so this is just, we will shortly be coming out with a new calibration with a larger data set, but here's an MCMC analysis histogram, which yields a value of the Hubble constant, again, of 73. This is based on a calibration, the Benedict et al. Milky Way, the LMC distance based on that calibration, and MC 4258. And this is Dan Spolnick's SuperCal sample, and I've just shown here the first set of CSP1 data from our sample. And that's about to increase by a factor of 6, sorry, it was a factor of 6. A big effort was made to fill in the redshift distribution that we had from the earlier CSP. Most of the objects that turned out to be feasible using the 1 meter telescope were at lower redshift, and so we wanted to move up higher redshift where the peculiar velocity effects would be lower, and so we have done that. Okay, systematics. So where are the challenges? There are a number of them, and I'm going to go through those fairly quickly now. Reddening and effects of metallicity, crowding, I've alluded to these, the 0-point calibration of the Cepheids. Do we live in a low-density part of the universe? We're only sampling a local Hubble bubble, and then small into the calibrators. Reddening is now, I think, a very simple issue to deal with. Involves getting data over different wavelengths. This is something early on we saw. If you measure the distance, the distance modulus function of inverse wavelength, you measure in the blue part of the spectrum, you end up with a higher distance modulus than when you go into infrared, and you can fit this with a standard extinction law. And when you have now Spitzer data into the mid-infrared, then you almost have no correction for reddening at all. But a couple of bands usually is sufficient to measure the reddening accurately. Metallicity, this is something that we've been able to get tighter constraints on since the KEY project. And for example, so the red points here are the LMC, blue are the Milky Way, and this is Spitzer data or ground-based H-band data. and this is W, a color that is defined to be reddening free. And so these are metallicities that have been determined directly spectroscopically. These are iron to hydrogen abundances. And so this is the difference from the mean period luminosity relation of stars in the galaxy and Milky Way as a function of Fe over H. And there really is very little effect. If you go to the infrared, or if you correct for reddening, it turns out to be a very small effect. So if it stayed in the infrared, that turns out not to be a big effect.
So when you start out with that, it seems like that W, which is close to 3, there's a small range of velocity. There's a big change towards the air parts over the day. So there's a lot of what's going on there.
So in the atmospheres of Cepheids, you have line blanketing that's caused by differences in metallicity. And so there is some effect, you can calibrate it.
Well, you can put one seem like they aren't consistent with each other, like a large vacuum in terms of their individual air parts.
So in fact, this is a version of the plot I'm noticing now. I think I'm showing one that doesn't have error bars, so it looks like the boxes, but I think actually the scatter is consistent. And I'm showing a version of the plot that I didn't need to show. Those aren't error bars. And so it is actually consistent. Crowding, something I mentioned earlier. So in the case of the Large Magellanic Cloud, so here's an image. This is a 6-degree scale. If you find the samples away from the bar, which is fairly crowded in our studies in the bar, or will particularly concentrate on the bar, then crowding really isn't a serious issue. But as you go, so this is now a 1-degree scale, as you go to 4258, and the scatter is larger, and then, as I said earlier, as you go even farther away, finding Cepheids becomes a problem. So you're really pushing the limit at HST at this point. And so you want a number of high-quality distances, and that's something that needs to be addressed. Parallaxes, just to give you quickly, this is the Hipparchus satellite, which now has been superseded by Gaia, which is headed to the micro-arc-second level of accuracy. Nearby Cepheids are going to have 20 to 30 micro-arc-second parallaxes very soon. I want to step in and then we've got our Lyra stars and Timid Red Giant Branch. I want to move on to those now as a check on Cepheids. So just to summarize, when Gaia is complete, we're going to have less than 1%. This is sigma pi over pi uncertainties out to several kiloparsecs. So the formal uncertainties in the Cepheids, the Lyras, and Timid Red Giant Branch are going to be much less than 1%. That's just going to fade away as an issue. So they did come out with a sample, first data release in September. There are a billion stars which we have positions in and early astrometry. And this, just to remind you, is what the HST sample looked like, for which we have multi-wavelength data. And we've been observing a sample of nearby stars in anticipation of Gaia. This is what the sample looks like now. So it's certainly not going to supersede what we have from HST at the current time. And this is a sample that has uncertainties less than 50%. So we're going to have to wait on them. There's really not anything much we can learn yet, except to say, again, it's consistent. You don't see anything really serious jumping out at us for the calibration, but we will do much better. That's coming soon. In terms of constraints on a local bubble, this is something that Adam and Dan looked at in some detail. And essentially, here they're changing the minimum, the range over which they determine the Hubble constant and slide along, moving that window. And they've also looked at models, and the chance that you have a deviation that's greater than 1% looks very small. So it doesn't appear to be a serious systematic. numbers of calibrators, that's something that I think we're going to be able to improve when we're able to measure distances, not just with the Cepheids, but using giant branch stars. So just a quick summary of where we are. I think reddening and the local effects of living in an underdense region, we really don't have to worry about it at the percent level. But we will have independent checks on the velocity, the crowding, the zero-point calibration, particularly with Gaia, and we will increase the numbers of calibrators. So that's really been the focus of the Carnegie Chicago Hubble program. And so we've been using Magellan, HST, Spitzer, and soon to be Gaia and JWST. And as mentioned, we have a robotic telescope, 2.3 meter or a 300 millimeter TMMT, not to be confused with TMT, which is 30 meter. But that's operating at Las Cajonas every clear night. And we've been observing a sample of 1,000 giants and 55 Lyrae stars. Here's our group, and one is a little nicer here. You may recognize these characters here, Dylan and Taylor. And what we're doing effectively is using stellar astrophysics as a probe of distance. So we are using Cepheids, but we are checking them with tip of the red giant branch and our Lyrae stars. Our Lyrae stars are these low mass analogs of the Cepheids, also pulsating variables. So just briefly, this is a method that's been around for a while. In fact, it's what Shapley used to determine the extent of the Milky Way. It's not widely realized, but he used the bright giants in globular clusters. And halos of galaxies contain a number of red giant branch stars, and Vada referred to this as a red sheet that suddenly dissolved when he observed M31 when the lights of Los Angeles were down during World War II. They changed the distance scale. It's a really simple technique conceptually. It has a strong physical basis. These are so we can observe in the halo. The contrast here, you can't see the actual objects that I showed you in the previous frame. But what happens is that when you observe, this is the luminosity of magnitude here is a function of color or effect of temperature, essentially. And you can see by eye. You don't even have to measure to know that it's there, but we can quantify it very accurately. But essentially, these are stars that are evolved stars. They left the main sequence. You have the main sequence, you're burning hydrogen to helium, you exhaust the hydrogen, and the star collapses, and eventually the core is held up by degeneracy pressure. And then you get burning in a shell around the core, and the star climbs the giant branch here. Temperature rises, and as the mass of the core increases, the temperature is increasing, and ultimately you break the degeneracy. So when you reach about 10 to the 8 degrees, you get what's known as the helium flash, and you break that degeneracy, you have more phase space, and in a matter of hours, temperature goes up to about 10 to the 9, but it's absorbed by the other layers, so you don't even see it observationally, but you do see this guillotine, this change in density, which you can quantify. It's now been applied to hundreds of galaxies locally. This work by Dylan Hack here on a nearby galaxy IC1613. And the way you can do this is these are image analysis techniques that are well known. There's something called the Sobel filter for finding edges. And essentially you can convolve, in this case, we observe a giant branch, it's a log number, with a kernel of some form here. And then you get this spike that can be very well quantified, and you can measure the tip. And so empirically, it's very simple. Theoretically, we understand it well. And how does it work? This is the comparison now of the distances obtained using Cepheids and tip of the red giant branch. And so out to 20 megaparsecs now is where we pushed it. You can see the movement is really quite good. So 18 galaxies now, and eventually we're going to HST and JW eventually. I think it's going to prove an important technique for constraining the uncertainties in H0. Here's our 300mm robotic telescope. And as I said, we've been routinely observing a sample of stars in anticipation of Gaia. We started this year before launch, but we knew that Spitzer would be gone, and we needed to do that ahead of time. These are the HST parallaxes for the RLRs, and here's what we get for Gaia, which is actually more promising right now than for the Cepheid, but that will get better. And here's a preliminary tip of the red giant branch for the giants in the Milky Way based on Gaia. And you can see these are sigma pi over pi values. It's already a huge step increase compared to Hipparchus. In terms of what we can do already with HST, in terms of numbers of calibrators for the supernovae, and so here's the answer being shown here, and tie into the Hubble flow and the 0 point that we will get ultimately from Gaia, which I think shows that H naught to 1% is actually a feasible goal in the near future, and this is just by a tip of the red giant branch. A huge advantage with JWST, first of all, you've got an increase in resolution, so you get a greater volume that you can survey, but the red giant branch stars in the H band actually become much brighter. So here's a 10-day Cepheid in the infrared, and this is I band where we've been doing measurements to date. So that also is going to improve. And these are the stars, as I said, that are crowding the Cepheids. So by observing in the halos of the galaxies, crowding is much less, and the resolution of JWST is much greater. This finally is just a comparison of where we were in terms of known systematics at the end of the key project, and the different improvements over the last few years. The parallax sample from HST, Adam Reese's group that's been observing supernovae and increasing the numbers of supernovae, the Spitzer observations that test the optical data, and then our anticipated Gaia JWST, which will not only have a Cepheid 0 point, but also an independent check to the red giant branch and our Lyrae. And so percent level accuracy plus precision, I think, is coming very shortly. So I'm going to end here and say that I think there's been huge improvement again in what we can do in measuring distances. I think we have a ways to go to establish that there aren't still systematics at the percent level, but we've got a mechanism now for addressing those. And with Gaia and JWST coming up, increasing the numbers of calibrators, correcting for systematic effects, removing the 0 point uncertainties, moving into the infrared for both Cepheids and supernovae, and I haven't even had time to talk about efforts here that Josh Freedman is leading in terms of gravitational lensing determinations of H0 with EES, LIGO sirens, that Dan Holtz is potentially poised if LIGO electromagnetic detections of LIGO sources happen in the near future. And so I think there's reason for real optimism that H0 to 1% is feasible. I'm going to stop here. Thank you.
Thank you very much, Wendy. We have time for questions. Dan Skolnick. You have a loud outside voice,
Yes.
but I need to walk all the way back there.
Wendy, so you showed a plot from like a Burns-Freedman plot of possibly new supernovae, and is that a new result with a new H0?
That's actually a result that we got a couple years ago. It's an unpublished plot. We're adding to that now because we have a much bigger sample of supernovae, but we were looking to check that so this was the CSP sample of supernovae, and just looking to check the consistency with your work, Adam's work.
So could that be considered another?
Yeah, it's a completely independent calibration. And so again, right now, you don't see a way with the known systematics to explain the discrepancy of the Planck. Our two groups get essentially completely consistent results with the uncertainties. So if there is something lurking, it's something we don't know about.
Carlos.
So you mentioned mentioned a series of possibilities that might explain the discrepancy based on the fact that the CMB results are based on a model, but I didn't see any compelling way of moving it. So imagine the discrepancy still persists. Is there anything, any convincing argument what could be the reason of it?
I think some form of, either an extra species of neutrino or some other kind
But
of.
that will large structure will be affected by
Yeah,
that.
I mean, there was some combination of parameters that will,
That's what.
You can turn that knob.
yeah. And it's one of the only ways we're gonna know.
Well, I thought the only added nothing else, then it does increase the page.
Yeah, but there are
Does the
many
global,
ways that you
does the
can
global
do.
fit improve?
Sorry?
The global fit improves by adding an additional relative species.
Well, you have to tweak something out, I mean, something else would. But
So
it's
maybe I
perfectly
can
allowed,
shorten-
it's perfectly allowed, it's not ruled out is the better way of saying
I see an expert in the second row. And can I sharpen Carlos's question for our expert in the second row? So is there a tweaking that would bring the Hubble constant to 73 without screwing something up? Because I think that's what Carlos and Leanne Howe were trying to say is, clearly you can make the Hubble constant go to 73 with the microwave background, but you pay a penalty. And so is there something that leads to a really good fit and H naught equals 73?
Nothing compelling, nothing where all of the data is pointing in the same direction. So, you resolve some functions a little worse than other things like BAO. So,
Yeah, so BAO, if there are systematics there, or, line and alpha turns out to point out a problem in the galaxy data, we just, at this point, we don't know. So there are ways to resolve it, but when you correct that, it would have other implications.
I didn't mean to hand the thing to him, because I want to ask you a question on the thing that you're expert on. So George Estaffiou regularly talks to God. He has assured me of that. And the Hubble constant is 67. And so where do you think it is here?
So really, I'm agnostic on this. I don't think.
I wasn't asking about your religion. I was asking where do you think the weak point is? Where would you?
I would turn it around, because if you measured H naught to 1%, I would ask him what would change. And clearly you would get a fit, it's a non-unique fit. And so I think it's up to us to chase down the systematics. I mean, the key project, what happens is, if there are systematics at the 1 to 2% level, they're hiding right now. And so once we can get around this issue of the 0 point, and we have tests of the Cepheus to the red diamond branch, and we have several checks with RORism into the red diamond, then I think, it'll be clear. There are either unknown systematics that will uncover, or we're going to increase the accuracy and it'll come down. But I don't see any indication of it. Adam and Dan don't see any indication of it. So it's something we don't understand right now. But I think what's really good is that we're going to have the facilities to check that it's happening, so that it's solvable.
So I guess what you said was, and it was one of the themes, I just want to make sure I understand it, is that you don't see anything. You kept saying, we got this better data and it's going to get better, but we don't see anything. So you would go with the Donald Rumsfeld unkunks.
Yeah.
Okay, great. So we got Steve and then Don Lamb, and then we're going to have to go to the students.
So at the risk of lightning bolt from Mustafi, I wonder if...
He's God, I'm not, but...
Right, so is there a single thing, is there a kind of thing that you know of in the CMB experiments that would lead to this effect and fix some of the tension? And the things I'm thinking of are, for example, probably with the beam at high L's, or problems at low L's, which are difficult for all of these experiments. So are there things, if you wanted a knob that included experiment, do you know of one that is a single?
Yeah, if
single thing?
somehow the high L data turn out to be more reliable, then you would get a higher value spin it. But again, the low L data may be pulling it, the L is lower than 30. And the 19 says, no, they just don't see anything. But we'll see.
So I think we're, each of us thinking about this, we know something about, worrying about the type 1A supernovae that I know something about. One thing I noticed where future will be that at that time, systematic and statistical errors in the type 1A supernovae will be the largest contributor to the error for each node. I'm just asking, even if right now, how confident are we that 0.03% is really accurate as to the systematic plus statistical from type 1?
So I think if you're going to address systematics, you really do need independent ways of coming at it. If you only have one way, you can't assure yourself that you've covered all the systematics. So I think the types of systematics that we know about, things like reddening, things like metallicity, we can look at with multi-wavelength data, and those data are getting better. Right now, we're at a point where the statistical uncertainties are pretty comparable to the systematic uncertainties. But the systematic uncertainties are going to go down. We can test, for example, when we get a...
Like, what about the templates? There's been conflict with the templates. That's at a very large level. There's been conflict between the templates that are used to try to infer views distance modeling that are fairly large level, and that's separate from the observational systematics directly, statistical. I'm thinking about things like that.
So, many different groups have been looking at this, and they have different methods for fitting templates. In the end, you chug it through the machinery, and the uncertainties really, they're smaller than 3%. So you have to treat everything in a systematically consistent way, but in the end, it doesn't have a big effect on the result. But yeah, there are different ways of approaching it. But in a sense, that's good. People come at this from many different ways of fitting techniques. But we will also be able to look at the scatter in the TRGB Cepheid calibrators, and that will be some indication too. But so there are questions of, are the supernovae and ellipticals and spirals different? And that appears to be the case. Luminosities actually are different. So the TRGB will get at this question of the ellipticals. You can't do that with the Cepheids. So again, there are these kinds of couple percent effects that we'll be able to tease out that we can't do right now.
So this is a really exciting story, and we haven't heard the end. But let's thank Wendy for a fantastic